Hello everyone, it is Physics40S. This is Unit 7, Lecture number 1. And it's Dr. Carroll here. I hope you're having a nice day. Unit 6 was all about electrons staying in clumps of regions in space, right? Electrostatics, buildup of electrical charge. Unit 7 is all about the electrons moving, currents, especially in solid state. In liquids, you can have protons moving as well. Same in gases, but we're going to focus mostly on solids, though mathematically we do pretend that it is the protons that are moving. That is known as the conventional current, and the electron flow is just in the opposite direction because protons are positive and electrons are, that's right, negative. So we're using our booklet here. We're on page 31, and let's look at the definition of electrical current. So the symbol we use is capital I, and current is something moving per time, right? When we talk about a current in a stream, how much water is moving past a point per second. That's an example of a current. We're talking, though, about how many electrons pass a point per time, or how many protons pass a point per time. The flow of protons is called conventional current, sometimes abbreviated CC. The flow of electrons is called the electron flow, and it is opposite in direction to the conventional current. So current itself is a vector. We don't usually make a big deal about it, but it is a vector. And the units for current are amperes, named after some guy, Andre Ampere. And an ampere is a coulomb per second. Ampere is one of the base SI units, along with meters, kilograms, and seconds in the MKSA units. So very important, ampere, coulomb per second. We sometimes hear milliamps for smaller electrical appliances, but things like vacuum cleaners, they're running on, could be like 12 amps, right? The more amps, the more powerful the vacuum cleaner is, and we're going to get to a discussion about that a little later in this chapter. So the equation here for current, I, is Q divided by T, or cross multiply the charge delivered somewhere is the current times the time. So Q equals times the time. Q equals IT. One way to remember this is think of the word quit, but you never quit, so there's no U in quit. So stay current and write it as Q equals IT. So let's look at some examples of this equation. The equation actually, if you're really interested, comes from calculus. Some of you taking calculus are going to. We'll look at calculus as current as the rate of change of charge with respect to time, so dq by dt. But we're just looking at an average value, q divided by t. So suppose there's a reference point and you have 5 microcoulombs passing some point in 4 minutes. So the protons are marching through some place and you're counting them, and you could get exactly how many protons there are by converting microcoulombs to protons. But we want to get coulombs as our numerator in I equals Q over T, so 5 by 10 to the minus 6 coulombs, because micro is 10 to the minus 6, and per second, so 4 minutes, well, you can do that in your head, I hope, 4 times 60, 240 seconds. So the current associated with this process is 2.18 by 10 to the minus 8 amps, Q divided by T. Okay, so that is example 1. Now, in the second example, let's say you have 4 picoamps, so that's 4 by 10 to the minus 12 amps, flowing for 3 hours. How many protons would march by? So Q equals I times T. Pico, 10 to the minus 12, so 4 by 10 to the minus 12 amps, 3 hours. Remember, an hour is 3,600 seconds, so 3 hours is 3 times 3,600 seconds, and you get 4.32 by 10 to the minus 8 coulombs. Then we can convert that into elementary charges. One elementary charge is 1.6 by 10 to the minus 19 coulombs, and you get 2.7 by 10 to the 11 elementary charges, which means 2.7 by 10 to the 11 protons. So that's another style of question. Third one, how many days does it take for 7.2 moles of electrons, remember a mole is 6.02 by 10 to 23, to pass a point if the electron flow is 2.8 milliamps. So here we're solving for time. So time is Q over I. Always cross multiply and say Q equals IT. So the charge, let's see, I got 7.2 moles. Each mole is 6.02 by 10 to 23 electrons or elementary charges, because each electron is 1.6 by 10 to minus 19. Now notice I'm just taking the absolute value here. Okay, that works. Divided by 2.8 by 10 to minus 3 amps. So you get 2.48 by 10 to the 8th seconds. Then you can convert that to days. So 2,870 days is needed to have that many moles of an electron pass a point. But the current is small there, right? 2.8 milliamps. So those are the varieties of questions for just looking at current. And there's a worksheet you can download. I believe it's in the website, called Clarinet, which is all about current. It's either at the end of a Unit 6 package, or else separate, or else part of Unit 7. So you can find it, and once you find it, put it on ESB where you found it to share it with other people. It's like a little passenger hunt in search of electrons and current, okay, as we're looking at current events, aren't we? So let's say, okay, it's great to have electrons flowing or protons flowing, but what can we do with those? What's so useful about that? And well, what's useful is we can have them flow through a circuit and they can do work. So a circuit is something that has electrons flowing through it. A open circuit means the electrons stop flowing through it. A closed circuit means they do flow through it. A short circuit means they're flowing through it too quickly and too much heat is generated and you can end up with a fire. When you think of circuit, you think of things that are closed. If someone's a speaker for some company and they're going to a bunch of different cities doing a speaker circuit, right? They're going to different places and then coming back to where they started from. In French, circuit is home run in baseball, right? So you start at home plate and you end back at home plate. So I think that's interesting. Anyways, we're talking about electrical circuits here. Currents flow through them. An electrical circuit is the closed path through which electrons or protons travel. We talk in this chapter about direct current and a tiny bit about alternating current, but our big focus on direct current. Next chapter is alternating current. Direct current is unidirectional, so only one way. So a 9-volt battery is a source of direct current. You can plug in things to your wall outlet, and then diodes and adapters will convert alternating current to direct current depending on what your electrical appliance is that you're using. So the components of a direct circuit, you have a power source, a conductor, it's going to be copper, aluminum, gold even, switch so you can have control over when you want the circuit to come and not come or not, and a load, something that the circuit is flowing through. Could be a light bulb or something, an air conditioner, a speaker, all sorts of things. So here's a schematic diagram, and we're using circuit symbols in my schematic diagram. And whenever you buy an appliance, it'll come with a schematic diagram, usually on the last page of the manual. And I know usually you take your manual and just put it in some drawer somewhere and never see it again. But you should save those, especially if you have to return something, right? So here's just an example I made of a schematic diagram. So we have the cell here. We've already looked at this a little bit. The longer line is the positive, and the shorter line is the negative terminal. And then we have current passing through this circuit, and we have control by a switch here. And this is a single throw, single pole switch. There's fancier kinds of switches, but this will suffice. And then I just threw in some components that we'll look at. A fixed resistor, which means it's an electrical component that offers a given resistance. It's fashioned that way. A variable resistor, which allows you to change the resistance, the flow of electrons through the current. For example, A rheostat is an example of that, a dimmer switch on a lighting, or a volume control on your radio. Those are examples of variable resistors. So the symbol is the same, the little jaggedy lines, but you have this diagonal line going through it. That means variable. Then, just for fun, I threw in a fixed capacitor and a variable capacitor. We won't really look at capacitors that much in this chapter, but those are components that are thrown in. A load here is a circle here. I made it like a lamp, and there you go. So your protons flow from the positive terminal to the negative. Electrons flow from the negative to the positive. And there's other schematic symbols that we'll look at. We have the ground, which is this symbol here. Batteries in series could be written like this. Batteries in parallel is different. Okay, so and we'll get to some of those other ones as we go through. So let's focus on resistance now. I see I snuck it here on the right on page 31. So resistance is the capital letter R, and it is the opposition to the flow of electrons. Okay, so every load in a system offers some resistance. Sometimes you want lots of resistance, like a heating coil in a hair dryer. You want lots of resistance, and then you have a fan which blows that hot air onto your head and dries your hair. Sometimes you don't want much resistance at all, like in a computer, and all the circuitry in a motherboard of a computer. You don't like heat generated, and you need a fan to blow away the heat. So ideally you want to use materials that don't offer much resistance. In a perfect world you would use a superconductor where there'd be no resistance at all, but no industrial room temperature superconductors have been produced yet. When that day happens, that'll be a good day. Okay, so resistance is opposition to the flow of electrons or protons. Insulators offer more resistance than conductors, and the resistivity, which is a Greek letter rho, R-H-O, it's not spelled rho like that, sort of this curly P here, is proportional to the resistance and is greater for insulators than conductors. Then there's something called conductivity, which is the reciprocal of resistivity, but we won't really talk much about that. But resistivity, we're going to look at some equations about that, and it's like a fingerprint for a substance. So again, insulators like wax would have, and certain plastics would have greater resistivities than something like copper or silver. Every load offers a resistance, and resistors are electrical components used to control the flow. And the unit of resistance is an ohm, named after a guy, George Simon Ohm, and the symbol is the Greek letter omega. So that's a convenient choice of symbols to use for the unit of resistance. So the more resistance there is, the less the current there is. Okay, so let's look at this law associated with this guy Ohm on page 32. An ohm, by definition, is a volt per meter, and if you want to go into the base SI units, it's kilogram meter squared per ampere squared seconds cubed. Okay, so that is an ohm. And Ohm's law says that the voltage is the current times the resistance. So the resistance is the voltage over the current. So for a given voltage, a given push, think of voltage as the push of electrons through a circuit, if I have more current going through there, then my resistance is going to be smaller. If I have less current going through the circuit, then my resistance is going to be greater. Do you want more? Do you want less? It all depends on what you want to do. So, but this law works in many cases. There are some exceptions to it, but in the vast majority of cases, Ohm's Law is a good way to discuss simple DC circuits and networks for DC circuits. How do we measure these quantities? Voltage is measured using a voltmeter. Some of you may have a multimeter at home, and you measure the voltage drop or the voltage across a load by putting the two leads so they're parallel to the load, not in series but parallel. And the symbol for the voltmeter is a V with dashes on either side. A is an ammeter, and it's measures the current, and it is put in series with the load. So where you want to get the current, you put in an ammeter. If you want a really sensitive ammeter, there's one called a galvanometer, which is a very sensitive style of ammeter, and it's a G in a circle. If you want to measure the resistance, you use an ohm meter, and it's that letter omega in a circle. And it is just placed wherever, parallel or series, wherever you want to get a resistance. So let's look at some examples of the application of Ohm's Law. And we'll start with a simple circuit, which means that there is just one load or one resistor put in. So we have here in the middle of page 32, we have 10 volts for my voltage. We have a current flowing through. We have a given resistance of 20 ohms. So we want to get the value of the current. So I is V over R, 10 over 20, and you get half an amp. So half an amp of current goes through, and it's going through the whole system. Some students think, oh, there's less current before you hit the resistor and more current after, or the other way around. No, it's as if the voltage and the resistor talk to each other, or the load offering resistance talk to each other, and then decide how much current to go through. There's a whole garden hose analogy about voltage is like the water pressure from the source. Resistance is the thickness of the hose, and current is how much water is coming out per second. So you can, if you really want to look at some videos, Professor Dave, etc., that use that garden hose analogy with current, resistance, and voltage. Second example, I keep the same voltage, or part B of this example, and I make the resistance less. Well, if I make the resistance less, I'm going to get more current flowing through. So it's still 10 volts, but now it's going through 10 ohms as opposed to 20, so you get more current going through. You get 1 amp going through the circuit as opposed to half an amp. In my third example, I'm going to have a lot more resistance. I'm going to have 40 ohms of resistance, so my current is going to be 10 over 40, or 0.25 amps going through in that case. Okay, so those are simple circuits. Now let's look at what if you have more than one resistor in series. Okay, so these are not simple anymore. We usually don't have more than 6 or 7 or 8 of these. So let's look. Resistors in series. So this is still on page 32. So here, classically, we're going to have 3 resistors in series. So your protons march through, and they go through resistor 1, resistor 2, and resistor 3, and then back again. So it's one path. Yeah, there's curves to the path, but there's one path only, one resistor after another. That is called in series. Some of you may have come across batteries in series before. So maybe even in junior high you looked at that, in grade 9 electricity unit. So the total voltage is the sum of the voltages delivered by all the dry cells to make your battery. So they're called cardinal rules actually. There's 3 rules about resistors in series. First is that the current, the total current, T stands for total here, not for temperature, not for period, but for total, is the same. If I put an ammeter near resistor 1, resistor 2, resistor 3, the total current is the same all the way through. The voltage delivered is the sum of the voltage across resistor 1 and resistor 2 and resistor 3. So you add the voltages across 3, you get the total voltage. This all stuff comes from something known as Kirchhoff, K-I-R, why didn't I write it out? K-I-R-C-H-O-F-F, Kirchhoff's law. So if you take some more circuit analysis in future courses, you're going to hear that phrase, Kirchhoff's law. Okay, and the total resistance, I can bundle up these three resistors in series into an equivalent resistance, which I can call REQ or R total or RE or RS, because this is in series. You'll see all those terminologies as you get into circuit analysis, and it is simply the sum of R1, R2, and R3. Okay. A way to prove that, Ohm's law works whether you're talking about simple or complex circuits. So the total voltage would be V1 plus V2 plus V3. But V equals IR, so I1 R1 plus I2 R2 plus I3 R3. But the I1, I2, and I3 are all the same. They're all I total, so I can factor that out. And my total voltage is I total times R1 plus R2 plus R3. Well, R1 plus R2 plus R3 has to be our total, because V total is I total times R total. So that's the way to prove that the total resistance is adding up R1 plus R2 plus R3. Okay, so let's look at an example here. Let's say we have 300 volts, and I know R1 is 5 ohms. I'm not sure what R2 is. I know R3 is 10 ohms, and I know the current is 15 amps. So we want to solve for what's going in. And I have what's called a severe chart. Oh, it's very serious, severe chart, but really just CI, VIR. And CI stands for circuit item. Some people call this whole process the circuit analysis game. They say, oh, if we call it a game, then the kids will find it more fun. Well, I don't know about that, but that's what some of the books do. So I got the circuit items, R1, R2, R3, and then R total. My total voltage is 300. I'm given that. Okay, so I'm given the 300, and I'm given, because I see it in the circuit diagram, the amps, 15, which means it's 15 amps for each resistor. R1 is 5 amps, and 5 ohms times 15 amps, so 75 volts have to go across R1. R3 is 10 ohms times 15 amps, so 150 volts has to go across R3. Well, if the total voltage is 300, and R1 is 75 volts, and R3 is 150, so add those together, it's 225, then R2 has to be 75 volts. And if R2 is 75 volts, and you know the current is 15 amps, then R is V over I. So I get 75 divided by 15, 5 ohms. And then you check, and you say, okay, 5 plus 5 plus 10 is 20. So there can be different orders in which you do these questions, and if you have time, you check your work by looking at different orders in which to get your final answers. So this is a classic example, example 1, and let's look at another one here. You don't always have to draw this on page 33. You don't always have to draw the circuits like as perfect rectangles. You can have them all curvy if you want, and that's what we have here on page 33. So I got 4 resistors, And here I labeled them with letters. You don't have to label them with numbers. Most of the time I use numbers, but letters are allowed to. So I got RA, RB, RC, and RD. Those are 4 resistors in series, and my voltage is 100. So that's given. And let's say in this, you're given the 4 resistors. Okay? So you're given the resistances, and you're given the total voltages. Now you have to fill in everything else in our severe chart. A key thing to do is to get the... Oh, someone's talking to me. Who is that? That is an iPad. I don't want to talk to you, Siri. Siri is very all-knowing. I think Siri, Alexa, and OK Google are having a tea party today or something. Anyways, if I add the resistors together, I get the total resistance. So as soon as you can get the totals of everything, voltage, currents, and resistance, the better you are at solving the rest of the questions. So I add the resistors together, 5, 10, 15, 20, so that's 30, 50 ohms. And then I can get the total current because I is V over R, so 100 divided by 50, and I get 2 amps. And once I get 2 amps, then I know that the current through each resistor is 2 amps, so all of these are 2 amps. And once I can get that, then I get V equals IR. This is like one of those Sudoku puzzles, isn't it? Which I can never get right. So I times R, so 10, 20, 30, 40. So when I check, when I add the voltages together, I get 100. So these are examples for resistors in series, and if you are into like finding these like old electronics, like you collect all that old junk, you can find some older motherboards where you can see the resistors in series, and they're little striped cylinders, and those colored stripes actually is a logarithmic way to say what the resistance is, and there's a whole code associated with those stripes. Okay. Resistors in parallel is another configuration that resistors can be, and there you have more than one branch. Think of resistors in series as being cars all on a one-line highway going one way. Okay, resistors in parallel is like the 401 in Toronto. It was like 8 lanes going each way. Yeah, what that means is the more resistors you have in parallel, the less the more your overall current. The more your overall current. We'll see how that works. And resistors in series, the more resistors you have in series, the less your overall current. So, because I equals V over R, so the more R, yeah, the less I. Okay, so parallel we have here in my first example 3 branches, and where the branches touch others is called a junction point. So I can put these little things here as junction points. So I got current going through 1 branch, 2 branch, 3 branch, and we'll keep it simple at the beginning and just have 1 resistor in each branch, but very soon we're going to look at more than 1 resistor in each branch. So the total voltage is the voltage across branch 1, which is the same as the voltage across branch 2, which is the same as the voltage across branch 3. It's like maybe you've been at Tinkertown or something where they have those super slides and there's different lanes and kids are going down different portions of the super slide. Okay, so there can be like 8 portions, but the green one is got more wax on it, so you're going faster, and then the red one's got sandpaper, so you're going slower. But you're still going from the top to the bottom, so the change in potential energy is the same. So you can think, hey, that's actually a pretty good analogy. I just thought of that. So the voltage is the same across each of those branches. The resistance doesn't have to be the same, and the current doesn't have to be the same. But when you add the currents together, I1 plus I2 plus I3, you have to get the same total. It's like cars going 3 different pathways, but when they all converge at another place, then outside of the branches, coming back near the source, the amount of cars that went in the 3 different ways converging back, so you just have the same amount. So the total current is I1 plus I2 plus I3, and you can prove that to get the equivalent resistance, 1 over R total, you do this on your own, 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3, and I'm not going to bother with that other method. Okay, so in our first example, we have, let's make an example here. Let's have the total voltage being 12. So in my severe chart, my total voltage is 12, which means my voltage across each resistor in each branch is 12 volts. I will give you the resistance of each resistor, the value 2 ohms, 4 ohms, 6 ohms. By the way, unless otherwise told, the voltage is going to be in volts, the current is amp, and the resistance is in ohms. And if it's different, I'll let you know. But in a severe diagram, that is our default set of units. So we get a total resistance of 1.09 ohms, because 1 over R total is 1 over 2 plus 1 over 4 plus 1 over 6, which becomes 11 twelfths. So our total is 1211, so 1.09 ohms. If you don't like doing fractions, then punch it all into your calculator. But fractions will be handy at times to get these equivalent resistances. So now that I know that the total resistance is 1.09 ohms, notice that it is less than the resistance of any of the individual resistors in any of the branches. And that has to be the case because the reciprocal relation here. If you get the total resistance and it's more than any of those resistors, then you've made a mistake. So make sure it's not. So you got the total voltage, 12 volts. You got the resistance, 1.09 ohms. So my current is V divided by R, and you get 11.01. And now you can get the current through each of the other ones. Through resistor 1, it's 12 over 2, it's 6 amps. Through a resistor 2, it's 12 over 4, it's 3 amps. And third one, 12 over 6 is 2 amps. And notice how when you add the amps together, you get 6 plus 3 plus 2, you get 11 amps. So it works. And in this second example, I decide to add another resistor in parallel, an 8 ohm resistor, go through everything, and look at this. The current goes up. The resistance goes down to, oops, sorry about that, to 0.96, and the current goes up. See, there's one more path for current to flow. And this is how we overload our circuits, how we blow a fuse in our circuit at home, which are wired parallel. If you put in too many appliances, then your equivalent resistance, parallel equivalent resistance, sometimes written RP, is going to get smaller and smaller. And if it gets smaller, you're going to be drawing more current. And there's only so much current you can draw from your power supply before you get overheating effects and dangerous stuff happens. So your circuit breaker gets tripped if you plug in too many appliances. So you want to be careful on that, and especially, I was just looking at this the other day because my basement is freezing. These heaters, these portable heaters, don't put them on with any other appliance. Have them their own dedicated circuit, and don't use an extension cord either, because that can, or a power bar. That's bad news. So those portable heaters have to be treated with respect, because they take up a lot of current. They draw lots of current. So if you hooked up 3 in parallel, you're asking for big time trouble. And hopefully there'll be safety switches, but not all of them have these safety switches. So the more resistors you put in parallel, the greater is the current. As an aside, the voltage V is sometimes called electromotive force, EMF, or sometimes even curly E. I don't like to use curly E for it because we use that for electric field, but you sometimes see that. Okay, I'm going to find some practice questions for you on these pure series and parallel, but just go over these ones on your own. And the network of resistors, well, let's hold off on that one and do that one as lecture 2 for unit 7. Okay, sounds good.